What happens when you add both donors and acceptors to a piece of silicon together? When an electron moves to a place where there is a hole, the electron may take its position. The process is known as recombination. At the site of a donor atom, a positive charge is left behind at the atom core after the electron moves away. At the location of an acceptor atom, the core atom becomes negatively charged after the state represented by a hole is taken up by an electron. The entire system, however, remains neutral and the electronic configuration is the same as undoped silicon. Therefore, when both donors and acceptors are added, they can cancel out the effects of each other instead of adding up the number of carriers. When dopants are added to the system originally at thermal equilibrium, it suddenly increases the number of one type of carriers. Let's use donor type of dopants as an example. Assume 10 to the power 15 per cm cube of donor dopants are added. Holes can more easily find electrons to recombine so that the recombination rate is increased. As the newly added electrons significantly outnumber the amount of holes, the number of electrons will not change much, but the number of holes will be significantly reduced until a new equilibrium is achieved. It has been found that the equilibrium condition is achieved when the product of the number of electrons, N, and the numbers of holes, P, is equal to the square of the intrinsic carrier concentration. Or mathematically, the equilibrium condition is achieved when P times N equal to the square of Ni. Now, we can do a more careful calculation for both the numbers of electrons and holes. For an N-type silicon material doped with Nd, assume that there will finally be P holes in the material. Then, we have the number of electrons N equal to P plus Nd because each hole also corresponds to one electron. At equilibrium, we have P times N equal to Ni squared. That means we have to solve for P from the equations P times P plus Nd equal to Ni squared. As the majority carriers are dominated by carriers from the dopants, Nd is much larger than P, and we can just assume the number of electrons or the majority carriers is just equal to the number of dopants. In that case, the number of minority carriers, P, can be calculated by the square of Ni divided by the doping concentration.